Okay, guys, this is the last phase of your suffering. Nothing afterwards. Promised. Maybe. Okay, so now it's this inverse calculation business. Is we want to go the other way around. Figure out what are the properties of the particles given their IOPs. So just like we did in radiative transfer, the radiative transfer calculation with hydrolyte, in hydrolyte you put IOPs in. In hydrolyte we put IOPs. No, the wrong color. You guys don't like it and I don't like it either. Okay, there is a big chalk. I don't know. Yeah, there is. Okay, so in hydrolyte we put IOPs. We have hydrolyte. And then it generates for us RRS or light fields, whatever you want. This is the forward calculation. There's always, we know there's always one solution and it's going to give it to us. And depending on if it's garbage in, you get garbage out, but if it's good in, you get good out. The inverse problem is always ill-posed because there potentially could be many, many different solutions, and we're narrowing it usually down by looking for a physical solution or when it makes sense. So this is the inverse. The same can be done, this is forward. With MeCodes, it's exactly what we're putting is the microphysical properties of the particles. This is how they like to tell it in atmospheric science. But we can call it whatever else we want to call it. It's the properties of the particle. It's its size, index of refraction, which is another way of saying composition, etc. I mean, or this certain aspect of it. And we put it into a MeCode. And then we get out of it IOPs. The inverse calculation is to go, I measure IOPs, can I tell me something about the particle I'm under investigation? And this is, for example, what Rebecca Green did with the flow cytometer. So here we'll assume we have a culture of diatom that we ran through the AC9. And we got an absorption of 0.14. Okay, my A is 0.14 inverse meter. And it's a culture of a diatom. Independently, I got an undergrad because they're usually the one counting cells, and had the undergraduate count individual cells to tell me how many there were in my dish. And this undergraduate who works for me said, 5 times 10 to the 5th cells per ml. So these are the numbers. And I'm measuring with lambda at this is at 676. And now I'm going to ask you to find n prime. Tell me what's the n prime that's consistent with this. What's my n prime? What's the imaginary part of the index of refraction based on this information? So how would I solve it? I can do a bunch of forward calculation and find which one will give me the correct n prime. So A is, remember, it's QA times cross-sectional area pi d squared over 4, sorry. Do I know something about the D? It's 4 micron, lucky me. So I know something about the D. The D is 4 micron. And this is times concentration. This will be my A. So from this, I can get QA. And then I can vary n prime in my anomalous diffraction code. For example, the one I gave you, but you can do it with the Excel spreadsheet until you get it. And since the anomalous diffraction approximation, n prime does not depend on n, you don't have to know n. Or you just have to know n prime. You can change it until you get the right QA. So let's calculate what it is. QA will be 0.14 divided by pi. D is 4 times 10 to the minus 6 square, D square. All this divided by 4. So this is the big division here. And I have to divide by concentration, which is 5 times 10 to the 3. So that's 11 cells per liter. Yeah.
What does that do?
What I'm doing is I'm starting with a number of 1. So if I had 1 particle here, if this was 1 particle per meter cube per micron, if I had 1, I'm calculating what beam attenuation would be. Let's say I had 1. I got a beam attenuation of 0.0003. But I measured